In class, we talked about partially observable Markov decision processes, and one of the important properties of POMDPs was proven by Sondic, and that is that the value function over belief space, or the probability distribution over states, is piecewise linear and convex, meaning that it consists of a series of linear segments and it's sort of cupped upwards like this. And that means the value function can be represented as the maximum over a set of linear functions of the linear function of the belief. And in class I gave an algebraic argument for why this is true, and that actually is the argument that Sondic used. But I want to step you through a geometric argument that I used in my dissertation that I think is really useful. So if you think about t-step behavior in a POMDP, you can represent any behavior as a kind of a policy tree. So any behavior has to start off with some action. Then what happens? You take the action and you observe one of the possible observations. Once you've observed that, normally in a POMDP you update your belief state and then you use that belief state to decide what to do next. But really what's happening here is you take an action, you make some observation, and then depending on what that observation is, you take some next action. And then again you make some observation and you take some action, and this continues to a depth of t steps. So any behavior you might want to adopt as a function of an initial belief state has the form of one of these policy trees. How many of these policy trees are there? Well, there's just a finite number because there's a finite number of actions, and the size of this tree is finite. And we just plug in each hole in this tree, we plug in with one of the actions. So there's just a finite number of structures like this. And what you want to do is figure out for the current belief state which one is best. But one of the cool things about a policy tree is that the value function for a policy tree is a linear function of belief. And why is that? Well, for each possible state that you might be in, remember belief state is a probability distribution over the states of the underlying MDP. And for each of these possible states, if you execute a policy tree from that state, you get some expected reward. And since a belief state is a probability distribution over these states, the expected reward of a belief state is the expected reward over all possible states of executing that policy tree, weighted by the probability that the starting state is one of those states. So as you change this belief state, it simply changes the probability distribution over states, but it doesn't change the expected reward for starting in each of these states. And so we're really just taking different convex combinations of these expected rewards. So a policy tree induces a kind of a vector where the components of this vector, one for each state, is the expected reward for executing that policy tree starting from that state. So what I'd like you to do is to use this concept to answer the following question about a particular POMDP. So let me tell you the POMDP. So we're going to mix metaphors here a little bit and base this POMDP actually on a little bit of game theory. So I think we talked about the Bach-Stravinsky game, or the Battle of the Sexes game. It's played between two players. They each independently choose an action, either Stravinsky or Bach. If they both choose Stravinsky, then they get non-zero reward, with player 1, the row player, getting a smaller reward and the column player getting a higher reward. And if they both play Bach, again they get non-zero reward, but this time with the row player getting the higher reward. And this is supposed to model the idea of the two of us are going to show up for a concert together, and we'd rather be together than not be together, but I, the row player, likes Bach better, and you, the column player, likes Stravinsky better. So now what we're going to try to do is to develop a two-step strategy for playing against one of two possible players, either a player that chooses Bach or Stravinsky completely at random, or one that chooses Stravinsky all the time. And in the beginning we don't know which is which, but we do have some probability distribution, B, that the probability that we're playing against a random player is some value x, and that we're playing against the always Stravinsky player is 1 minus x. Now a policy tree in this game is going to be for us to choose some strategy, either Bach or Stravinsky, some action first. Then we get to observe what the opponent did on the previous step, either Bach or Stravinsky. And then we get to condition our second action on what we saw. So it could be that after we chose Bach, then we saw the opponent did Bach on that round, and then we juice Bach again on the next round. Could also be that we start with Bach, and then we see the opponent do Stravinsky, and then we play Stravinsky on the second round. So this is a two-step policy tree for this game, which, by the way, is a POMDP because of the hidden information about which state the opponent's in. So now the question is, this policy tree, which we'll call BBS, because there's three different slots for actions, and we filled the first one with B, the second one with B, and the third one with S. So I'd like you to give a value of X for which this policy tree is actually the optimal policy tree to take. There's going to be, it turns out, several different possible policy trees that are optimal for different values of X. But this one is optimal for some range of values, and I want you to give one of the values from that range.